All right, let's go ahead and get started. So we talked very briefly about this idea of a Taylor series last time, and this idea of we want a function. So some continuous differentiable function. I want it to completely agree with a polynomial, even if the thing I'm trying to fit to it is not a polynomial. So we talked about this idea here. By completely agreeing, what does that mean? Is it enough for a point to agree? No. Is it enough for the first derivative and the point to agree? No. So really the thing we're trying to build up here is this series where they agree at a point, and also every derivative, every order, approaching infinity, those derivatives agree as well. So that's essentially going to be how we build up what these coefficients are. First of all, it's been a few days. Any questions about the motivation? If I can condense what I just said into one sentence, I'm trying to make any differentiable function look like a polynomial. So now let's try to do this. Let's try to generalize kind of what these coefficients look like. I know that C naught is equal to f of 0. I know that C1 is equal to f prime of 0. I know that C2 is equal to f double prime of 0 over 2. C3 is equal to f triple prime of 0 over 6. Is this enough? Can I generalize from here? Or do we need to go a little further? What patterns do you see kind of as what I want to do is this. I would love to build a sequence C sub n based on this function. So what patterns do we see emerging as I'm kind of building up from C naught to C4 that'll continue as n grows? So f prime of 0, f of 0, f prime of 0, f double prime. What am I doing with those? What are these are all based on f, but they're not all f. What am I doing with these functions here? Taking the next order derivative, right? So that's going to be part of this. Is I'm going to take the nth derivative at 0. So I think that covers what's going on in the denominator. Can I generalize what's happening in the denominator? So what's that? N factorial. Does that make sense? And I think I didn't write out like how we found all these derivatives, but is that gonna, like, let's say let's look at the next term. So let's take a few derivatives. What's the first derivative of x to the 5th? By x to the 4th? What's the second derivative? 20x cubed. And then 60x squared. And then finally 120x. So if I'm going to take what's having to do, so 1, 2, 3, 4. But basically, how am I finding all these coefficients? First, I multiply by 5, then I multiply by 4, then by 3, then by 2. So I think that is the behavior that we follow when we take a factorial of some whole number. So do we agree with this thing here? Is this thing going to work for any value of n? Okay, so this is essentially how you build a Taylor series. So again, the purpose of these things is I want to approximate any function with a power series or a polynomial. And the way you construct it is like this. So Hopefully this looks familiar to the thing we just built. There's one subtle difference here. The function we just built in the last slide was centered at x equals 0, right? In reality, you can build a Taylor series around whatever x value you want. That's represented by a there. But still the same thing. I want the function I'm trying to approximate to agree completely with this polynomial. So they need to share a point. They need to share a first derivative. They need to share a second derivative, and so on and so forth. So before we build a few of these, I want to make sure we understand what the point of this construction is, how it works. What questions do you have? Okay, so let's give one a shot. Oh, so I keep calling it Taylor series. How many terms are in Taylor series or in any series by definition? Infinitely many, right? So that's a little impossible for us to deal with. In many cases, we'll deal with Taylor polynomials, which means I'm going to say so many terms are good enough and cut it off there. Another name to throw at you is really, so Taylor series is a very general thing. Or at least in one respect, the Taylor series is always built this way, the way that I've underlined. A Maclaurin series is a very specific Taylor series, which is centered at 0. So if you see that name Maclaurin, we're still talking about Taylor series, but we're giving you a specific detail. So we're centering on x equals 0. Shall we? Okay. So f of x equals e to the x is not a polynomial, but I can hopefully approximate it with a polynomial. So I need some information. So to build out a Taylor series, I need to know the value of the function, the value of some derivatives. Actually, let's do this in general first. F of x equals e to the x. What's f prime of x? E to the x. What's f double prime? Okay, so would we agree that every derivative of e to the x is e to the x? Okay, so from there, we should be able to build out these things. What's f of 0? 1. What's f prime of 0? F, so these are all going to be the same as well, right? So these things right here should allow me to build out the Taylor series. So let's be very general about that. I want to build the Taylor series for this function. That'll be f naught plus f prime naught, or sorry, f prime of 0 plus f prime of 0 over 2 plus f prime of 0 over, let's write this, 2 factorial, 3 factorial. I'm not being careful with my derivatives. But this is what my Taylor series is going to look like, right? So what's my first term going to be? 1 plus, there's something very crucial I left out of this thing up here at the top in the margin. I'm not taking my powers of x. So what's the second term going to be? One plus 1x plus x squared over 2 plus x cubed over 6, and so on. Let me generalize that. So I got to stop writing down terms eventually, but if I can condense them all into a sigma notation, that'd be good. Can we do that? What's happening to the powers of x from term to term? Increasing by 1. And how about the coefficients? So the coefficients are 1, 1, 1 over 2, 1 over 6. I believe the next one would be 24. Should be 1 over n factorial. So I believe my Taylor series for f of x equals e to the x is this. So let's stop there for a second. Go ahead.
How did you get values like 1 and x squared? Like from what?
That comes from, so remember that this series we just built, even though it's maybe not obvious, probably not obvious, this is what e to the x is, even though e is not anywhere in that polynomial. So this all goes back to the idea of I want e to the x to equal this t of x thing, where t is a infinitely long polynomial. So what does that mean for them to totally agree? That means I want, so for whatever value this is centered at, and I said Maclaurin, so what does that mean? That means
center of 0.
Yeah, that means a equals 0. So that means I want these functions to agree everywhere. F of 0 equals 1. So let's do this. Let me unbox this so we have it's more clear. Here's my t of x, my polynomial. If I plug in 0 for x, what do I get out of this polynomial? Should be 1, right? So we talked about the derivatives of e to the x. Those are pretty easy to talk about because all the derivatives are the same function. Let's take the derivative of this polynomial. What's the derivative of t with respect to x? Derivative of 1 is 0. Derivative of x is 1 plus x plus x squared over 2. Is this looking familiar? So we said that e to the x has the same derivative over and over and over again, right? So would you agree that the first derivative of our Taylor polynomial is identical to the Taylor polynomial itself? So that's another way that you can see that they're kind of mimicking each other. But now let's do this. If I take the first derivative and evaluate it at 0, what do I get? Should still be 1, right? So we could do this with any number of derivatives, but you're still going to get to the same place of all those values being the same. So that's how we build this out. And in general, this thing I wrote up in the margin is, that's always going to be how you're going to construct that polynomial. Okay, so we said that this thing is equal to this infinite sum of x to the n over n factorial. Any more questions about how we decided that or how we built that up? Now what I would like to do is figure out if this approximation is any good. So I would like to find out where it converges. So how can we find that out? Do the ratio test. So the thing we've built is a power series. We've just done it in a very specific way. But because of that, I can do the ratio test. So x to the n plus 1 over n plus 1 factorial all over x to the n over n factorial. How does that simplify? Absolute value of x. What happens with the factorials? I have I believe this is what remains, right? So I want to know where this converges, so I'm going to force it to be less than 1. So what is the limit of 1 over n plus 1 as n gets very, very big? 0. So I get 0 is less than 1. So it does not depend on x, essentially. The x gets annihilated. So what does that mean about where this series converges? It converges for all real numbers. So x, if x is a real number, from negative infinity to infinity. So basically this infinitely long polynomial is not an approximation for e to the x, it is identical. They're exactly the same. So this is not guaranteed to happen for every function, but for e to the x it does. So again, questions about the thing we built, how it's done, what we have now that we have it. Are we okay? All right. So now let's look at a Taylor series that's not centered at 0. Okay. I'll let you all decide where to start. What kind of things do we need to build this series? Let's get a first few derivatives. So if f of x equals e to the negative x, what's f prime of x? Negative what? Negative e to the negative x. What's the second derivative? E to the negative x. E to the negative x. So the second derivative is equal to the function. Did we already find, like, is that the full list of things it'll do? What's the third derivative? Okay. Can we agree that's just a cycle? It's going to alternate back and forth. Okay. So we have like this 2 cycle. It's just going to bounce back and forth between e to the negative x and negative e to the negative x. Cool. So we got the function and its first 3 derivatives, but really we can find any derivative we want to because we understand the pattern that's emerging. That's an excellent first step. What can I do from there? Remember, when we build the Taylor series, we're kind of stuck to. So with the e to the x, we said that this series that we found, the x to the n over n factorial, that is going to be true no matter what x you choose. But when you build a Taylor series, you have to choose a single value of x to kind of construct the whole thing on. So we chose what single value of x for this one? 0. And how about this one? 2. Okay, so What do I do with this value now that I have basically all these derivatives? What's that? Right, so now I want f of 2, which is e to the negative 2, and f prime of 2, which is negative e to the negative 2. And those are going to be the only two values we get, right? Okay, so we're getting a little more specific. We got several derivatives with respect to x. Then we plugged in our center value of a equals 2. We can say everything we want about the derivatives at those points. Now what? Maybe I should remind you all what this thing looks like for a point that's not 0. So f of a plus f prime of a times x minus a plus f double prime of a times x minus a squared all over 2 factorial. Hope that's enough as amount of space. So given that, can I start filling in what the Taylor series is? What's the first term going to be?
E to the negative 2.
E to the negative 2, followed by
Negative e to the negative 2 times x minus 2.
good. Moving on. Plus e to the negative 2 x minus 2 squared over 2. I'll do a fourth. Minus e to the negative 2 x minus 2 cubed over 6. So any questions on how we got the first 4 terms there? Should we write some more terms, or do we think we can generalize? So if I can condense all this stuff into a sigma. So what patterns do we see emerging? So one thing that's always going to be there is this term, the x minus a to the power of n. But what else is there?
It alternates.
It alternates. So I'm gonna throw in my kind of standard alternating term. Does that work? Or does it do, why? Does that work, or is that gonna do the opposite of what I want? It is worth making sure that it alternates in the way you want. That should be okay. So negative 1 to the n times x minus 2 to the n. What else? Over n factorial. Is that enough? What's that? I don't think we're done with the Taylor series. Yeah, so there's going to be e to the negative 2 in here as well. Lots of different ways to write it. Maybe I'll do this. Over e squared n factorial. Or would you rather keep it as e to the negative 2? Okay. So e to the negative 2 will always be there. It just alternates, right? X minus 2 is incrementing by 1s. Its powers are incremented by 1 and are divided by n factorial. We okay with that? Okay, so I think that's a good Taylor series. All right. Now that I have that, can I find the radius of convergence? So let's take a look. So again, ratio test. So -1 to the n plus 1 times x minus 2 to the n plus 1 over n plus 1 factorial times the reciprocal. So all right, as I'm writing this all out, what simplifies? Okay, so that's what's left. That's what cancels. Okay, so x minus 2 to the n cancels. And I think that means the n, this is just to the power of 1, right? So you said this cancels. But I have an absolute value, right? So I think that -1 is going to just, its behavior is going to go away as well. So let's start, let's do that for now. So I have x minus 2 times e to the -2 over n plus 1 factorial times n factorial. All right, good. Anything else that can be done? So the n factorials, when they simplify, what happens to them? Okay, so absolute value of x minus 2 times e to the -2 over n plus 1, and I want that limit to be less than 1. Oh, you're right. Thank you. All right, so what is this limit? What happens with this limit? Goes to 0. So what's my radius of convergence again? All real numbers. So lots of ways to say all real numbers. So another one where I have conversions everywhere. As long as I have infinitely many terms, I use the whole Taylor series, I get convergence everywhere. Questions? But
We reach that conclusion with like any sort of either the escalator.
let's think about it. Let me ask you this question. What in the series like really makes that convergence go to, or like let me ask it this way. This ratio test went to 0, right? What really caused that? So in our kind of manipulations in our algebra, what really caused that limit to go to 0? This is the factorial, right? The fact that my series involves a factorial in the denominator. So do you believe that would always happen if I'm dealing with an e to the something function? So in the short answer, yes, it will. If you have e raised to like a linear power, we had x and negative x, that will always happen. So exponential functions will converge everywhere. Okay, how about a trig one? All right, how would you like to start? Fun derivatives. So what is the first derivative of sine of x? Cosine of x. Second derivative? Negative sine of x. Third? Negative cosine of x. And fourth derivative,
Um,
sine of x. Is it cyclical? Well, the next four derivatives look to be the same as these four. Okay, so I think that's enough. These are general functions. I would like to evaluate them at some place. Where would I like to evaluate them? 0. What is the sine of 0? 0. What's the cosine of 0? 1. What's the negative sine of 0? 0. And I think that's the full list, right? Those will cycle. Okay. Good. That's some good data. Now what?
I could be
Not for the first derivative. So let me write this very generally. Okay, so we're going to have a lot of 0 terms, right? So we might have to look out a little farther to help us generalize. What's the first term that's non-zero? Should be x, right? F double prime was 0, right? So what's F triple prime? That's going to be -1 times x cubed over 3 factorial. Let's go get one more. So I think the next one's going to come from the fifth derivative, right? The fifth derivative should be, what's the fifth derivative of sine of x? It's not alternate, but it does cycle. So yeah, the fifth derivative of sine of x is the same as the first derivative. So it's cosine of x. So that's going to be 1 times x to the, what derivative was I talking about? Fifth. So fifth power over what? 5 factorial.
And that like every 2, it will alternate between -1 and 1.
Oh, sure, that is true. Yeah. Does that help us define this Taylor series? We can do it. We got to be a little more careful. What's happening with the powers of x? They're increasing by 2. So I think because of that, we're going to have x to the 2n. Is that good enough?
You also call it the -1 power and working power. Those are just positive that first would be like 2.
So I got -1 to the 2n times x to the 2n over what? Is n factorial good enough? Two n factorial? All right, how do we feel about this thing? I think it's a good start, but it needs repair. So does the alternating term do what I want it to do? What does it actually do? It does not do anything. I'm always squaring it, right? So that's going to just be 1. So I don't want it. I want 2n to be the power. What do I really want? Is n good? Is the first term positive?
And minus.
N minus one, or I think N minus one or N plus one are both equally good. I just need it to alternate in the opposite way, right? What's that?
You can also go to zero. For this we don't throw any to zero.
I think we should, just because Taylor series are pretty much built that way.
Then one
So then,
following would be used with N.
and should it be N? You all sounded very confident that it was N plus one. Do we think it's minus one to the N? What will, let's not even worry about the first term. What will the sign be? SIGN sign of the first term in this series. The way I've written it in the sigma notation. Positive, right? Is that okay? Okay. Will the second term be negative? Okay, I think negative one to the N is fine. Is X to the 2N doing what I want it to do? No. 2N plus one? I think if it's just 2N, the powers on X are going to be 0, 2, 4, 6. Now it should be 1, 3, 5, 7. So I'm going to get all the odd powers. Is that okay? How about the 2N factorial? Should also be 2N plus 1. Okay, I agree with all that. How are we feeling? We would like to do the ratio test to see where this thing converges, right? Do we have any suspicion about how that's going to go? It's going to be all real numbers again, why, right? So the fact that I have a factorial in denominator means that the ratio test is going to deliver a 0. So I will, if you're not convinced, is that a star? Try again. Not too much better. So I'll leave this star here if you want to convince yourself, but I will say that yes, this is going to converge for all real numbers again. But if you're either not convinced or feel like some more practice with the ratio test would be worthwhile, go for it. But yeah, anytime you have that factorial show up in the denominator alone, I don't want to say anytime, but it's usually a good indicator that that's going to converge everywhere. Is that a question, Munia?
Is it so like for all one series gonna be all our numbers?
I don't know if I want to say that. There are some that, let me see if I can jump to one that will not behave the way you think. I think this one converges. I think this one does not converge everywhere, but we'll have to find out. How we doing? Any questions on this one before I leave it behind? Okay, so it's getting a little more complicated. X cosine X. What would we like to do? What's that? Yeah, so we need derivatives, so product rule is going to have to apply here. But one thing I want, maybe this will help us. I know that A is 0, right? How do I know that? McLaurin. Okay, so if A is 0, let's talk about this. What is F of 0? Zero, right? All right, so let's get some derivatives. What's F prime of X? Cosine X plus or minus X sine X? So product rule, the derivative of the first function times the second, so 1 times cosine X, plus the derivative of cosine X, negative sine of X times X. What's the second derivative? Negative sine x. And then what? Do we agree? Derivative of x is 1 times sine of x. Derivative of sine of x is cosine of x times x. Does this simplify at all? X cosine x minus 2 sine x.
That'd be negative.
Yeah, thank you. Do we see any patterns coming out of this? Here's one thing I know that'll be useful. I know the derivative of x cosine x, right? So I can just drop that in here. Negative cosine x minus x sine x. Minus the derivative of 2 sine x minus 2 cosine x. Does that simplify for me at all? Minus 3 cosine x plus x sine x. Right, do we see any patterns coming out of this? I got 3 derivatives, maybe we should write down some terms. What's f prime of 0? 1. What is f double prime? 0, right? What's f triple prime? Negative 3. Do we have any intuition?
For the next one.
What's that?
For the next one.
Question?
So when will this class end?
9:55.
Uh-huh.
9:55.
And 50?
Uh-huh. All right. Sorry, what were we talking about?
What's the pattern?
Oh yeah, do we see one?
Yeah.
I'd be a little bit surprised if we did, that we had confidence.
We have to do the rest, but maybe we'll alternate between like 0 and then the integers will be like alternate between like negative and then 5/2.
See if that happens. So if Munya is right, this next one will be 0, right? What do we think? 3 sine x plus sine x.
Yeah.
I think plus x cosine x. That looks like a 0. So this is 4 sine x, right? So 4 cosine x.
Plus x cosine.
Product rule. So derivative of x is 1
Yes.
times sine of x. Okay. If you think I'm wrong, let me know, because that's very possible. But the derivative of 4 sine x is 4 cosine x. I've taken this derivative a couple times now, so I'll just drop it in. So plus what? What's the derivative of x cosine x? Did that fit the pattern that Munya was suspecting? Sure seems like it. All right, are we okay with that? That is what's going to happen in the future. The seventh term is going to be, sorry. The seventh derivative term is going to be -7. That will continue on in the future. So, what the heck is this thing? Can we define it now? So the Taylor series, first term should be 0, or first non-zero term should be x, right? Then -3x cubed over what? 3 factorial?
Plus 5 x to the fifth, 5 negative 5 factorial.
Okay. If we generalize, then what happens? So what's happening to the powers of n? Increasing by 2. So is 2n plus 1 fair? That should give me the denominators, right? What else is going on in the numerator?
And it's the same as last time, where it's like x to the power of 2n plus 1.
Okay. And the denominator? Two n plus 1 factorial. I like this, but can we simplify it at all? I think there's one revision we can make here.
Get rid of the 2n plus 1 and make it,
Ooh, what does it become though?
Um,
Just 2n factorial? I think that makes sense. So x to the 2n plus 1 over 2n factorial.
what about the alternating negative?
Oh, that's a good question. How do we deal with that? Is -1 to the n good enough?
-1.
I think -1 to the n is going to do what I want. Because I want the first term positive. And what do we think that one's going to do? What's a good radius for conversions there? Should be all real numbers again. All right. So we built out a few of these Taylor series, Maclaurin series, talked about where they converge. Any questions on how to construct these things? At least as importantly, why we're doing it. Are we okay? All right. Let's go ahead and stop there. A couple minutes early, and yeah, we'll pick this back up on Wednesday.
Back,
I did, yeah.
last time,
Yeah, I got you.